In studying functions and their graphs up to this point, we may have noticed that in all of our examples, we've had two variables that change with one another in those problems. What if we have three variables, though, that are changing in concert with one another? How do we handle that algebraically, and how do we handle it graphically, and how do we interpret the situation? Well, that's what we're concerned with in this segment. Consider this problem. Suppose an object is propelled at a velocity of 48 feet per second on an angle of 45 degrees. So here's that object propelled at an angle of 45 degrees at a rate of 48 feet per second. Now we know that this object is traveling, we can think of it as traveling horizontally and vertically at the same time. Now, it's on an angle right here, but it's generally moving to the left and it's moving up. Now this is nothing more than separating the vector into its components. Now from trigonometry we know that that's accomplished using trig ratios. And the horizontal rate associated with this situation is found by using the cosine of 45 degrees, because cosine of 45 degrees is the adjacent side over the hypotenuse, so it would be r over 48. And the vertical rate, r subscript v, I can indicate it as, is found by using the sine ratio. The sine of 45 degrees is r over 48. Okay, let's do that, and let's talk about let's introduce the notion of time here in conjunction with this. All right, horizontal rate is cosine 45 degrees, which is r over 48. So r then is 48 cosine 45 degrees, but cosine 45 degrees is 1 over root 2. If I rationalize here, I'll accomplish a nice little cancellation, and I'll remove the fraction. Here's what I mean. This becomes root 2 over 2. I get the cancellation here, so the rate then is 24 root 2. Now I can associate this with another variable, time, by using the distance formula. You know, we're talking about a horizontal rate here, and so the distance formula, distance is rate times time, comes into play. Now the rate is 24 root 2 times time. Now if we're talking about a horizontal idea, horizontal distance, that's what x is all about when we talk about the xy plane. So x then is 24 root 2 times t. Now consider vertical rate. Vertical rate is sine 45 degrees, which is r over 48. So r then is 48 sine 45 degrees. Sine of 45 degrees is also 1 over root 2. We get the same rationalization, the same cancellation. The rate then is 24 root 2. So now this is a vertical rate at the moment that this object is propelled on that angle at that certain velocity. But immediately, gravity will begin to take its effect, and that object will slow down and then descend back to the earth. Now the formula relating that idea, that is height in relationship with time and this initial velocity, is this. It's h equals initial velocity times time minus 16t squared. And by the way, this is derived from one of Newton's laws. So initial velocity, well, that initial velocity is this vertical rate you see that we talked about. That's 24 root 2. And now just bring down the other elements. Now since we're talking about a height here, a vertical distance, you see, that's just a y idea. So vertical distance is this expression. Now we have two equations, and both of them, this x equation and this y equation, both involve time. So we have a variable x, a variable y, and a variable t. And what are we going to do with these? Well, it turns out that the two equations that we're talking about for x and y are called parametric equations. And the variable in both of those equations is t. And so t is called the parameter involved in this situation. Okay, let's see how we can analyze this. The parametric equations are these two equations. Now one way to deal with it, one way to analyze it is like this. We can make a table of values involving the three variables. So we could let t take on various values, and we could plug those various values of t into the separate equations. So if t is 0, then all the terms go out and x is 0, y is 0. If t is 1, then the x equation becomes 34, the y equation becomes 18. You see, so when t is 1, x is 34, y is 18. This means that after a time of 1 second, the horizontal distance is 34, the vertical distance is 18. You see, and then for a t of 2, x turns out to be 68 and y turns out to be 4. Now, we could actually plot the coordinates for the x's and y's, you see, on a coordinate plane, and we could attach to that graph information about time. We could say at this point t equals 0, at this point t equals 1, at this point t equals 2. Now, notice that in thinking about the passage of time, though, we create a certain linearity involved in this whole study. That time begins at 0 and there's a passage of time, and then there's a last moment for our study in this problem. So there's a certain orientation to the graph. That is, the graph has a certain flow to it in a certain direction, and that's kind of an important idea. And by the way, the graph is called a plane curve in this situation. Now, another way to deal with all of this, and in such a graph like this, we could read the graph and we would have all 3 bits of information at one time. But another way to deal with it is to take the 2 parametric equations and go through a process of eliminating the parameter. That is, we could actually eliminate t. And to do that, we take one equation, or one technique for doing that. I'll show you another one a little bit later, but one technique is to solve for t in one or the other equation and then substitute that information into the other equation. In this circumstance, it's easy to solve for t in the first equation. So that's the first thing we would do. We would find t to be x over 24 root 2. Now take this information about t and put it into the second equation. So the second equation becomes y equals, you see, and instead of the t here, we put our information from the other equation. And instead of a t here, we put the information from the other equation. And when we simplify a bit, we find y to be x minus x squared over 72. Now, it turns out that the graph of this equation in the xy plane, you see, is the same as the information that we have here. The trouble with graphing that, though, is that we have no information about t. Now, what are we going to do about that? Well, the graphing calculator has all sorts of ways of giving us information about t and about dealing with parametric equations. Let's have a look. To enter parametric equations on the TI-83, press the button marked Mode, and we're going to select the parametric mode by cursoring down to where it says Function, and then to the right one for parametric. Press Enter here, and now we're ready to enter our 2 equations. The equations are entered in the same menu as before. We press y equals, and I have already entered the 2 equations. Notice the protocol here, the way the equations are listed. This is x subscript 1 in terms of t. So it's x as a function of t, and this is y as a function of t. The window settings, now the window settings will mean little to you at this point, but we'll be coming back to these settings from time to time. A t minimum of 0 and max of 2.2 means that I'm setting our time at between 0 and 2.2 seconds, you see, and the t step is 1/10, and we'll be changing that from time to time in our discussion here. The x minimum was set at -5 because I want a little bit of distance to the left of the y-axis, and the max is at 80 because all of the important events of our problem are over at that point. The y minimum is set at -5 because I'd like a little bit of distance below the x-axis, so we can see where the x-axis is, and the y-max is 22. All right, so that's just for your information. Here's the graph, and I'll press Trace. The 2 parametric equations are listed at the top of the display, but the most important thing is at the bottom. As I cursor to the right, all 3 of these variables are changing. And let's interpret what we have at this point for t equals 0.5. A time of 0.5 means a time of a half a second. Now, remember, we projected an object at 48 feet per second on an angle of 45 degrees, and we're saying here from the graph that after 5/10 of a second has elapsed, that object is 16.97, or approximately 17 feet downrange, or 17 feet horizontally from the point of departure, and the object is 12.97, or approximately 13 feet off the ground. You see, 13 feet vertically. Let's assume that we projected this object from ground level. All right, then we can discover or investigate for certain ideas here. We can investigate, for example, for the maximum height of the item, the item projected. And I'm looking for the maximum y value here. I have a 17.94 at this point, 17.97, 17.68. So the maximum y value I can get with this degree of accuracy is 17.97. So the maximum height is approximately 18 feet, and that's occurring at a distance of 37 feet approximately downrange and after an elapsed time of 1.1 seconds. So it's an interesting bit of information that we can gather from the parametric equation format. Here I'm trying to figure out how long it's going to take and how far it's going to be before the object reaches the ground again. And I'm looking for a y component, a vertical distance, to be 0. Here I have a vertical distance of 0.7. When I cursor to the right, it becomes negative 2.7 and so on. And so it's closer here, and that's occurring a little over 71 feet downrange after 2.1 seconds. If we want more accuracy, we can gain that by zooming in on certain points, but there is another way that we can achieve that. Before we investigate a little more accuracy, let's go back to the window settings, and I'd like to show you something. I want to show you what happens if we set the t minimum at 0.5 and then let's say at 1.5 and the graph. See, we're just getting a portion of the graph here and pressing trace. Here is t of 0.5, and as I cursor to the right, as far as I can go, I can't go any further than a t value of 1.5. And so it kind of limits the portion of the graph that we see, but it certainly gives rise to and reinforces the notion of an orientation in terms of our problem. It's kind of we have a start point here at 0.5, and we're going in a particular direction here to 1.5, and that's what that orientation idea was when we talked about it on the board just a little earlier. So this graphing aspect corresponds with that fairly well. Let's go back to the window and set the window back at 0 and 2.2 for the max. And let's change the step distance from 0.1 to 0.05 and the graph. And now as we trace to the right, we'll notice that the time is changing by 0.05 of a second each time I press the right arrow button. And therefore we may be able to achieve a bit more accuracy in maximum height and also total distance. Let's see, I've got 17.97, I'm going back 17.998, 17.94. Okay, the greatest vertical distance is this one, and it's right at 18 feet as we had expected. The time elapsed, though, is 1.05 seconds, and the downrange distance is almost 36 feet. And if I investigate for the distance that and time related to when the object reaches the ground again, I'm over here at a y equals 0.71. This is where I was before. And cursoring to the right, oh, this is still the closest that I can get to the object reaching the ground. So nothing has changed in this regard. Well, let's see if we can give ourselves a little more accuracy by making the t step, the time step, you see, 0.01, and the graph. Notice how slowly the graph is coming up on the display, and that's because the calculator is making an awful lot of calculations here in order to place the graph on the screen for us. And as we press trace, we'll notice that the time changes by 1/100th each time we cursor to the right. And so we are going to get a bit more accuracy here. Gee, I'm pressing the right arrow key, and this is as fast as we can move over the graph. So there is an awful lot of information involved in this situation. Well, I'm looking for the highest y value I can find. I'm in the 17.9s here, 17.998, 0.9999. Oh, I'm coming back down now. So 17.9999, and so on. This is right at 18 feet, and we notice that that's a downrange distance of 35.97, or right at 36 feet, and it's occurring after 1.06 seconds. So that's the information that we were after. I'm going to cursor over to the point where we're very near the ground, and you might think at this point that the batteries are low on my calculator or something like that, but no, I just changed my batteries. This is just as fast as we can go because there's such an awful lot of information here that we have to run through. But we can see the great value then, I hope, of parametric equations, and it is that we gain information about three variables at one time using the parametric format. All right, I have a y of 0.38, a y of 0.04, a y of negative 0.2. Gee, this is the smallest y value that I can get, and this is occurring after a time of 2.12 seconds and a downrange distance of 72 feet. Well, we've investigated about all we want to investigate here, but remember on the board a few moments ago we took out the parameter. We substituted between the two parametric equations, and we eliminated the parameter, and we came up with an equation. Let's examine that equation now graphically. I'd like to go to the function mode, and I want to enter that function, so I'll press y equals, and here the function has already been entered, and here is its graph. Graph looks a great deal like the graph that we had on board just a moment ago, and in fact the x and y components are very much the same as the xy components that they were before. The only thing missing is the time idea. And a lot of times when we are faced with situations involving three variables, we would like the information about that third variable, and that's the great advantage of parametric equations. As you might guess, in parametric equations, time, or t, is not the only parameter that is available to us or possible in these equations. Here we have a pair of parametric equations in which an angle theta is the parameter. We're going to graph these in just a moment, but let's examine some aspects of the graph, what we might anticipate here. We're going to let theta take on values from 0 to 2 pi. But because we're going through one complete cycle for theta, let's think about the values for x and y that we can anticipate, because a lot of times we want to set up our window before we actually look at a graph. Now, how would we set up our window for x minimums and maximums, y minimums and maximums, and so forth? Well, we know that for cosine, the cosine of an angle, those values will change from -1 to 1. So 3 times -1 to 1 means that x will take on values from -3 to 3. In a similar way, the sine of angles changes from -1 to 1 as well. And so 4 times -1 to 1 means that y will change from -4 to 4. So that allows us to set up our window. Now we're using radian mode here, and we're going to look at the graph in just a second. You know, if we want to, though, with this set of parametric equations, we could remove the parameter. We could go through the process of setting up an equation that is rectangular in form and look at that maybe at the same time, but maybe we could gain some insight about what we may expect from the graph of these parametric equations by looking at the rectangular equation. All right, let's go through that process. We take our two equations here, our parametric equations, and we solve them for something that they have in common. Now, we can't very well solve for theta itself, but we can do this. We can take x and solve it for cosine theta. That's pretty easy. Divide on both sides by 3 and we get this. For this other equation, we can solve for sine theta. Divide on both sides by 4 and we get sine theta is y over 4. Now, all we need is some relationship involving cosine theta and sine theta. Well, the Pythagorean identity gives us that very easily. So we take our Pythagorean identity and just pop the information in. Sine theta we know is y over 4, so we have y over 4 squared here. Cosine theta is x over 3 squared. Once we square, we see an equation that looks vaguely familiar. You see, this is the equation corresponding with an ellipse. Now we're a little more familiar, I think, from our experience with ellipses to see the x in the first numerator of our fractions, so I've rewritten here in a more familiar form. Well, from here we can make an analysis here even before we look at the graph. We know that the larger of the two numbers is the 16, and so our major axis is vertical here, and let's see, the a value is 4, the b value is 3 from the 9, you see. So we have all of that information right away. By the way, notice that if the a value is 4, gee, that means that from the origin now, and the origin is the center of our ellipse, we go a distance of 4 to our vertex points in both directions vertically. So we're going up 4 and down 4. That corresponds with the y minimum and maximum that we talked about a few moments ago. And the b distance, you see the distance from the center of the ellipse to the ends of the minor axis, that's a horizontal idea here. And let's see, so we're talking about 3 to the left of the origin, 3 to the right of the origin. So our x values are going to go from -3 to 3. Gee, that's exactly what we found over here. And that's no idle coincidence that we can make an analysis like this and have a corresponding idea with the parametric equations as well as the rectangular form of the two equations together. Let's take a look at the graph.
I've already reset the mode to parametric, and I have entered the equations as we would expect them to be entered. Now remember, we talked about how t, which is a theta value, changes. Now theta is going from 0 to 2 pi, but cosine theta is varying from -1 to 1. So 3 times that -1 to 1 means that our x values are changing from -3 to 3. And in a similar way, since the sine of theta changes from -1 to 1, 4 sine theta will change from -4 to 4. So the y components will go from -4 to 4. Now from that information, we might assume that our window settings need to be made like this, that the x minimum is -3 and the x max is 3, the y minimum -4 and the y max 4. Now let me go back to the top and talk to you about setting our theta. Remember, theta changed from, we were thinking from 0 to 2 pi, and 6.3 is approximately 2 pi, and that's why our setting is like this. Well, the graph then has this appearance. Now I want you to notice a horizontal elongation, and we mentioned a little while ago when we took out the parameter and investigated the equation, we said, gee, this is the equation of an ellipse that is elongated vertically, not horizontally. So something is wrong with this picture anatomically. So, but if we look at the way the window settings are composed, we can tell what that problem is. And it has to do with the fact that the ratio of horizontal and vertical distance is a little off base. Now, here we have a y minimum of -4 and a y max of 4, and that is giving rise to a vertical distance for the entire window now, the vertical distance of 8. We know that the horizontal distance is 1.5 times the vertical distance, roughly. So that total horizontal distance would need to be 1.5 times the 8 here, and 1.5 times 8 would be 12. So for this to be correct sort of anatomically, then we would have to have a total horizontal distance of 12, and therefore our x minimum needs to be -6 and the x max 6. So I'll make those changes, and now let's have a look at the graph. Well, this is certainly more as we would have expected. Let's press trace and see what happens here. Now notice t is 0, and I am cursoring to the right. And as I cursor to the right, the icon moves around and the x-y components are changing as expected and so on. But I want you to notice that as I continue to cursor around to the right, that I'm just cursoring to the right, and that little icon just keeps on going around, you see, and continuing until t arrives at 6.3. Now, if I change the value of t, or the t max, to let's say 8, and go back to the graph, and press trace. Now here I am at 0, and once again I'll go all the way around, and let's see what happens as I get to 6.3, or approximately 2 pi, and actually go beyond that. Now I'm just keeping the right arrow button depressed here, and we're rocking around our figure. And as I get to 6.3, then 6.4, 5, and so on, you see that the icon will just keep on going until we reach the maximum for our value of t, and it will just continue to wrap like this continually until we reach whatever maximum we have set. If we set a maximum of 100, for example, we just keep going around and around and around until we arrive at 100.
Here's another situation where the parameter is not time. It turns out to be theta once again. The graph associated with these parametric equations is called an evolute of ellipse, a rather interesting graph, as we'll see in just a moment. Now, in the previous problem, we were able to eliminate the parameter pretty easily by using a trigonometric identity. Well, here it's quite challenging to eliminate the parameter. You might take that on, try it yourself. You'll see what I mean. Now, before we go to the graph, though, let's think about what we might expect for values that x and y can take on. Now, we know that, again, if the cosine of an angle is a number between -1 and 1, and when we cube, we get a number between -1 and 1. So x will vary from -1 to 1. Now, the sine of an angle, also -1 to 1. Cubing gives us -1 to 1. You see values that are in that range. And 2 times -1 to 1 means -2 to 2. So y values will have as their range, or their interval, from -2 to 2. So we can, upon that basis, we can go right to the graph.
Here are the two equations already entered, and remember that since we realize that the values of x will be changing from -1 to 1, and the values of y will change from -2 to 2. We might be tempted to make our window settings accordingly, but from our previous problem, we know to be aware of perspective. And so when I set the window here, I'm looking at a y minimum of -2 and a y max of 2, giving rise to a total vertical distance of 4. And if that total vertical distance is 4, then I know that the horizontal distance needs to be 1.5 times that. 1.5 times 4 would be 6. So I'm setting the x min at -3 and the x max at 3 for that purpose. Now, it may be that we could allow the calculator to do this by setting this up in the way that we think it should be. That is -1 and 1 here, and then going zoom and then square, and then get some good results from that. But at any rate, it's important for us to be able to calculate this. Incidentally, the t minimum is 0, the t max is 6.3, because our angles are varying from 0 to 2 pi, and here is the graph. Rather interesting looking graph, isn't it? And when we press trace, as expected, the t of 0 corresponds to an angle of 0 in radian measure. And if I press the left arrow button, I can't go any further to the left, because my t minimum was set at 0, and I can't go below 0 for that value. And as I cursor to the right and go all the way around the figure, now I'm cursoring to the right, and the icon is moving to the left here, and then I continue to leave the button down to the right, and it just continues to go clear around the figure. And that kind of is the nature of parametric equations, that we have this linearity involved in it. Well, let's see, we have a t of 6.123, and if I keep the right arrow button depressed, we can go no further to the right, or we cannot increase the value of t beyond 6.3. Now, we could reset to cause it to go around and on top of itself and so forth, but we'll not try to do that at this point. Well, let's see. Suppose we want to change to degree measure. Now, we can do that by resetting in the window for a t max of 360, as though we're thinking of degrees, and the step I would make probably 10 degrees at a time. Now, suppose I forget that I need to change the mode of the calculator for this purpose? Well, I'll know right quick as soon as I press graph, because the graph will seem to make an appearance and have a mind all its own. And once it's finished with all these shenanigans, I will be reminded that I needed to go to mode and go down here to radian and then cursor to the right for degree, press enter, and now I'm ready to graph this. And here it comes up in a more familiar form. And as I trace, notice that I'm tracing to the right and I'm stepping 10 at a time with the value of t, and that's 10 degrees at a time. And so we're cursoring around as we would expect to in the degree mode. So the evolute of ellipse.